Systems of linear equations arise in a wide variety of applications and are one of the central themes in linear algebra. In this video, let's look at some applications of the systems of linear equations. The applications of the systems of linear equations are polynomial curve fitting, network analysis, electric network analysis, the traffic flow or water flow, the balancing chemical equation. In the first example, let us find a polynomial that fits the 5 given points. Since 5 points are given, we can fit a 4th degree polynomial function. If only 2 points are given, we may fit a linear line. If 3 points are given, we may fit a quadratic. Since 5 points are given, we are choosing a 4th degree polynomial. P of x as a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4. By plugging in these 5 different points, we get a system of equation here. And solving this system by any one of the methods, elimination method, substitution method, graphing method, or the determinant method, Jordan's Gauss elimination method, or the reduced row echelon form using graphing calculator, we can find the constants a0, a1, a2, a3, a4. Plugging in those values in your p of x, you get the equation. So this represents the 4th degree polynomial where you can find all those 5 points lie on this. Suppose if we are trying to find the reduced row echelon form using our graphing calculator, then we will enter all these values in the stat edit L1, L2. After entering all these values under stat edit, we will say take stat calc and take number 7, which gives the equation got in the previous case. You'll get this equation because your y is the 4th degree polynomial where the constants a, b, c, d, e are obtained by your graphing calculator. So this gives an idea of how to fit a polynomial using the systems of linear equations. The second example is network analysis. Network is composed of branches and junctions. Now here in this case, at this branch, you have got 2 outputs and 1 input. So the sum of this output must be equal to the sum of the inputs. Here 25 must be sum of x1 plus x2. Let's make use of this idea to solve network analysis. So here a flow chart is given, a network flow is given, and we are trying to solve this system using systems of linear equations. So we have unknowns x1, x2, x3, x4, and x5. So we have to consider these junctions separately. In the junction x1, it looks like there are 2 outputs and 1 input. So this x1 plus x2 must be 20. So we have at junction 1, x1 plus x2 equal to 20. The same way at junction 2, 3, 4, and 5, we can find the total input is equal to total output, and then use this equation, use this system, and take the augmented matrix to get the reduced row echelon form and solve for x1, x2, x3, x4, and x5. So the augmented matrix for this system will be this, and the reduced row echelon form can be obtained like this. Since the last row is true, here you have your x4 minus x5 is 10. Here x3 minus x5 is 10, etc. So if I'm treating x5 as a variable constant t, real number t, then we can find the value for x1, x2, x3, x4, and x5 in terms of this variable t. So since t varies, it is a real number. It can take any possible values. So taking all those different values for t, you get infinite number of solutions for this system. The next example is using electrical network. We are going to analyze the electrical network. An electrical network is given. Now, at each junction, we have to apply both the laws, Kirchhoff's first law and second law. At this junction 1, it looks like there are two inputs, I1 and I3, and there is one output I2. That is using the first law. Using the second law, the product with the resistance R1 I1 plus R2 I2 is 3I1 plus 2 I2. That is using this path. And then for the second path, we get another equation. So we have got three systems of equations with these unknowns I1, I2, and I3. Taking the augmented matrix and taking the reduced row echelon form, we can find the value for I1, I2, and I3 for this electrical network. The example 4 is for traffic flow or water flow. The water is flowing through a network of pipes as shown here in this diagram. We have a network. There are unknowns x1, x2, x3, x4, x5, x6, and x7. So treating these as junctions and these are the branches, we get a systems of equations. The question is, solve the system for water flow representing x1, x2, x3, x7. You have to find the water flow when x6 and x7 are 0. You have to find the water flow when x6 is 0 and x7 is negative 1000. So using the systems of linear equation by considering the input is equal to output at each junction, taking that in the reduced row echelon form, we get this matrix. So the last row here is true. So we have x5 plus x7 is 500. So solving this, we can say, suppose if x6 is for s and x7 is t, then you can find the value for x5, x6, x4, and all this. So in particular, when x6 is 0 and x7 is 0, we get the values for x6, x7, etc. by substituting the value for, since x6 is s and x7 is t, and these two values are 0, by taking s equal to 0, t equal to 0, we get different values for this. The last question was, we were asked to find the values when x6 is 0 and x7 is negative 1000. So substituting those two here, we get this as the solution. The last example is balancing chemical equations. Here, let us take this combination. It says that the sodium hydroxide reacts with sulfuric acid, yields sodium sulfate and water. So sodium hydroxide plus sulfuric acid reacts sodium sulfate and water. So this is not balanced. If we want to balance this equation, let us take these unknowns W, X, Y, and Z and then consider each atom separately. Sodium. When we consider sodium, there are on this side it is W sodium and here 2Y sodium. So those W and 2Y must be the same. For oxygen, here W oxygen, 4X oxygen, and 4Y oxygen, here 1Z oxygen. So that's what I have. So the same way for sulfur and hydrogen, you get two more equations. So we get 4 equations By taking this system of 4, we can find the unknowns w, x, y, and z. So when you take the reduced row echelon form, it looks like you have these equations. So by taking this as a whole number, instead of taking that as a fraction, if you want to treat that as a whole number, you may get z equal to positive 2, but by multiplying this by negative 4, you can easily say your z equal to positive 2, y is equal to 1, x equal to 1, and w equal to 2. So substituting those values here, we get this as balanced equation. This is how the systems of equations are used to balance complicated chemical equations. So in this video, we saw the applications of systems of linear equations in polynomial curve fitting, network analysis, electrical network analysis, traffic and water flow, balancing chemical equations. Hope you enjoyed watching this video on applications of systems of linear equations. Thank you for listening and thank you for watching. Thank you.